Alright, so this is my attempt at explaining section 6.3, which is a section on something called exponential functions. An exponential function, the x is usually in the exponent. So I'm writing the word functions, which means if I made a list of points of the relation or the equation that I see, no two points would have the same x's, and if I made a graph, the graph would pass the vertical line test. So basically we say the x, there's an x in the exponent, or in a exponent, and that makes this an exponential function. We're going to be graphing exponential functions, so here's some examples of exponential functions real quickly, nice basic ones. So like f of x equals 3 to the x. That's just your standard exponential function. The 3 is the base, the x is the exponent. Could do something like g of x equals e to the x. E is the number 2.718. So where this says 3 to the x, this says 2.718 to the x. These are similar. They're both exponential functions. They have x's in the exponents. I could make the exponent a little fancier, maybe like 2 to the x minus 5. That would still be an exponential function because the x is in the exponent. Or maybe something like k of x equals 4 times x plus 6. That's still an exponential function. I could get more exotic, and as we get into the section, we'll get we'll get slightly different exponential functions. One of the skills, or one of the things that we're going to be asked to do is we're going to be asked to make a table of values and sketch graphs. And when I go to do an exponential function, if I'm asked to make a table of values and sketch a graph, I look to the exponent. If the exponent is like these first two examples, meaning it doesn't have a plus or a minus with the x in the exponent, the table of values that I use to sketch my graph would start off with 2, 1, 0, -1, and -2 in the x column. So if I was asked to graph this function or this function, I would start off making a table of values, and in the x column I'd write the numbers 2, 0, -1, 2, 1, 0, -1, and -2. I'd find y's that correspond to the x's, and I'd plot the points and I'd sketch a graph. Probably use my calculator to make sure that my graph that I'm going to sketch is reasonable. And if the exponents were more complicated, like the exponents in this h of x and x plus 6, using this table, although it might give you an adequate graph, it wouldn't give you the best graph. You wouldn't see the features of the graph as nicely. If I'm asked to make a table of values and graph either of these two, this table I wouldn't use. What I would do is something similar to when we graph parabolas. I take the number that I see in the exponent and change its sign, put it in the middle of my x column. So if I was graphing 2 to the x minus 5, I change the -5 to a +5, put it in the middle of my x column, and then I'll fill in a second, I'll fill out the rest of the numbers I might put in the x column. Similarly, if I was graphing 4 to the x plus 6, the table of values that I might use, I'd put -6 in the middle of the x column, then I'd fill it out before I got my y's. For this one, for the 5 in the middle of the x column, I'm going to put numbers that are bigger than 5 and less than 5 to fill up the x column, so 7, 6, 5, 4, 3. Similarly, for this one, I'm going to put numbers bigger than -6 and less than -6 in my x column before I find out my y's. So for these four functions, if I was asked to make a graph of these by hand, using my, making a table of values or a table of points, these would be the tables I would use. These certainly aren't the only tables that would make reasonable graphs, but these tables, if you use those, you'll get a reasonable graph. Probably more reasonable if you've graphed exponential functions before than if you didn't. 5 points to make a picture is maybe not enough at the beginning. Maybe you might need 10 or 12 points at the beginning to really get a feel for how the graph looks, but at some point 5 is going to be enough, and I'll try to make 5 enough right from the beginning. All right, so I'm going to start the section now. The very first problem in the section is just that first function that I wrote, 3 to the x, or the first even problem in the section. And I'm asked to make a table of values and sketch a graph. So I'm going to do exactly that. I'm going to make a table of values and sketch a graph. And I brought graph paper today. You don't really need graph paper at all. Your graphs don't need to be that accurate. But to do part A of number 2, my table of values for this is going to be that 2, 1, 0, -1, and -2. And then I'm going to take each one of these numbers and plug it into 3 to the x. So that's my x's are the 2, 1, 0, -1, -2. My y's are, I can write f of x, doesn't matter, they're equivalent. I'm going to find out what 3 squared is, 3 to the first power is, 3 to the 0 power, 3 to the -1 power, and 3 to the -2 power. That's just changing the x in the equation for the 3 to the x to those 5 numbers. And now I'll get the y's that correspond. The first y is going to be 9 because 3 squared is 9. And that's going to give me the 0.29. So let me go ahead and plot that 0.29. The next point I'm going to get is 1 comma 3 to the first power, anything to the first power itself. So the next point I'm going to get is going to be the 0.13. Third point I get is 0 comma 3 to the 0, because anything to the 0 power is 1. I'm going to get the 0.01. The fourth point's the tricky one. You might be tempted to write -3, but 3 to the -1 power is not -3. If I did this on my calculator and did 3 up arrow -1, my calculator's likely going to give me a decimal, which I can change to a fraction. Not that you can really see that, but my calculator gives me 0.33333, which is 1/3. If I hit math after that and enter twice, it tells me that 3 to the -1 is 1/3, because 3 to the -1 is the same as 1 over 3 to the first power, which is 1/3. So the fourth point I'm going to plot is -1 comma 1/3, and 1/3 is just slightly above the x-axis. So the dot that I made, that dot's probably closer to 1/2, maybe it should be a little bit lower. But anyways, I go left 1 and up just a little bit over the x-axis. The last value I'm going to write is 3 to the -2, and 3 to the -2, if I want to write that with a positive exponent, is 1 over 3 squared. 1 over 3 squared is 1/9. So now I'm going to plot -2 comma 1/9. And 1/9 is even closer to the x-axis. So I go left 2 for the -2 and then up 1/9. And I'm just barely above the x-axis. So when I go to sketch this graph and I connect the points, if I would have imagined 2 more points, I'd maybe get a better idea. Like if I had a 3 up here, then the next point would be 327, and this part of the graph gets really high really quick. Exponential functions have a really steep slope in some sense. The next point, if I would have plotted it, 327, would be off my paper, and I can't even plot it. So the graph almost goes vertical after the 0.29. It shoots up really fast. However, if I go off to the left, the next point I would have written is -3, 3 to the -3 power, which is 1 over 3 cubed, which is 1 over 27. As I go to the left, the graph doesn't go down forever. As a matter of fact, the graph, the y's are always going to be positive. The fact that the y's are always positive, that means every point that I plot off to the left is going to be microscopically above the x-axis. And actually the graph is never going to touch nor cross the x-axis. So that I'm trying to emphasize that this graph is always above the x-axis. As far as I go to left, it stays above the x-axis. I'm going to go ahead and graph this function on my computer program, and then I'm going to really zoom in on this x-axis part so you could see that there's always a gap between the graph and the x-axis, but that gap, it gets really hard to see. So I'm going to graph 3 to the x on my calculator or my computer program because it has better graphics. I'm going to get a picture that looks like this. It's going to look like the graph touches the x-axis, but it really doesn't. And then I'm going to zoom in to show you that the graph is actually always above the x-axis. Assuming I actually get the program to work. So here's the function, insert function, 3 up arrow x, and I love with the dash line. Let me make it solid. Solid, and I'm doing red today, so red. So there's a picture, looks a lot like the picture that I drew, and you'll see that the graph goes forever to the left. And it does go forever up. It just goes off the screen. If I made my y-axis get bigger than 10, that line going up will keep going up and to the right forever. It'll never, it'll go all the way as far to the right as I can see. As a matter of fact, let me make the y's really big, just so you can see that the graph doesn't stop off to the right. Doing this, making the y's really big, is going to not maybe give the best picture, but it shows you that the graph keeps going forever and to the right, and it gets really high really quick. So this is already at 1,000 for its height, and it's not that far to the right, but a graph will keep going to the right forever and ever and ever. So now let me zoom in on the y-axis. When I zoom in on the y-axis, you're not going to see so much this part of the graph, but you're going to see the y-axis part really well. So I'm going to really, really hone in on the y-axis, just so you can see that the graph is always above the y-axis. I'm going from negative 0.0001 to 0.0001 on my y's. And what that's going to do is basically take a magnifying glass and put it on the x-axis. And when I do that, the graph over here doesn't even look like it's close to the x-axis. And let me just bump out the window a little bit then on the x's, make my x's go further to the left. And that's too far further to the left. So you can see now on this really, really magnified window that the graph really isn't that close to the x-axis. It's still above the x-axis. Let me just tweak the window a little bit more. Make my y something like negative 0.01 to positive 0.01, which is a little wider window. And when you see that, you start to see more of the graph. So the graph is always above the x-axis. There's always a gap between the graph and the x-axis. But in this window that I have now, you can't see the gap between -9 and the x-axis. But if I magnify that a little bit, then you can start to see the gap. That's probably a bit overkill. But the idea is, with these exponential functions, the standard exponential functions, this graph is never going to touch the x-axis. This is always going to be above the x-axis. This is an absolutely reasonable picture. This is completely everything I need for 2A. For 2B, all exponential functions, at least all the ones that we're going to get, to find the domain is going to be negative to positive infinity, because the graph exists all the way to the left and it exists all the way to the right going up. If I extended this graph to the right, it'd go to positive infinity, but if I've extended it always to the left, it'd go to negative infinity, 0. So going to the left, the x coordinates go off to negative infinity, but the y coordinates don't go under 0. Going to the right, the x coordinates eventually get off to positive infinity, as do the y coordinates. So this is the extension of this graph. And from that extension, I can do the domain. For the domain, I need the x coordinate of the far left point, which is going to be that negative infinity. And I need the x coordinate of that far right point, which is positive infinity. The domain of every exponential function that we're going to do today is negative to positive infinity. Or all real numbers would be another way to say that. For the range, the graph is always above the x-axis. The x-axis has the equation y equal to 0. I'll say the range is from y equal to 0 up to y equal infinity, because the bottom of the graph is always above y equals to 0. I'm going to have a 0 as the first number in my range. It's going to have a round parentheses because the graph doesn't touch the x-axis. And then for the top of my range, I'm going to take the top of the graph, which is y equal infinity. So for the range in this particular equation, I'm going to say the range is from 0 to infinity, that the graph is always above the line y equal to 0. And it turns out that this y equal to 0 line, if that the x-axis itself, it is a horizontal asymptote, which is a line that the graph approaches to as it gets way off to the left. So this line, the x-axis, which has the equation y equals 0, serves as an asymptote, which is a line that the graph gets microscopically close to, but never crosses or touches as it goes off to the left. So the y horizontal asymptote has an equation of y equal to 0. That's everything that's asked for problem 2. I'm going to do a bunch of graphs today, so eventually, if the parts B, C, and D didn't make sense, then maybe they eventually will. The part B, the domain of every exponential function we're going to do, is going to be negative to positive infinity. It's this part, the range and the horizontal asymptote, that might be a little bit tricky. And honestly, range is more of a calculus question. It's kind of a limit question in calculus, and we're not doing calculus here, so we do our best to try to explain the concept, without doing calculus. So this next problem's not in the problem set, but I wanted to graph e to the x. And graphing e to the x isn't really that different than graphing 3 to the x in terms of my table of values. So when I'm going to graph f of x equals e to the x, because the exponent is just x and doesn't have a plus or a minus in it, I'm going to use the table 2, 1, 0, negative 1, negative 2. And then that's for my x's. For my y's, I'm going to plug the numbers. I'm going to get e to the second power, e to the first power, e to the 0 power, e to the negative 1 power, and e to the negative 2 power. Unfortunately, every single one of these is not going to be, none of these other than e to the 0 are going to be nice numbers. And I'm going to round, and my graphs aren't that accurate. I'm going to round to 1 decimal. A lot of times I round to 2 decimals, but for graphing, I can't graph any more accurate than 1 decimal. I can barely graph 1 decimal worth of accuracy. So I'm doing e squared for my first y. I'm going to write 7.4, and you can write 7.39. It hardly would matter to me. But I'm going to try to graph the point 2 comma 7.4. I got that y by hitting second and ln, which gave me the e with an up arrow. Then I typed the number 2. I really can't see this today. And then I hit enter. So I did second and ln, and then I got 7.38 something something. So let me plot this point 2 comma 7.4. So I go over 2, up 7.4, and again, that's probably not perfectly graphed, but it's close enough. The 2 is fine, but the 7.4, and that maybe that looks more like 7.5, but it's close enough. Now I'm going to plug in 1 and go second ln e to the first power. That gives me 2.718, and I'm just going to write 2.7. You could write 2.72 if you care to, but can't really graph 2.7 that well anyways. So I'm going to plot the point 1 comma 2.7. So I go over 1, up 2.7. 2.7 should be closer to 3 than it is 2. It should be more than halfway. My point almost looks like it's halfway, so I'm not really striving for perfect accuracy here. Just something that's reasonably close. That's why I'm only doing 1 decimal as opposed to 2. Can't even plot 2.7 that well. That's looks more like 2.5 to me than 2.7, but it's close enough. For 0, anything to the 0 power is 1, so that's the only point that I don't need to rely on my calculator for. So I'm going to do 0, 1. And then the next two, e to the negative 1, second ln negative 1, I get 0.36, which I'm going to write round as 0.4. So negative 1 and 0.4, which is under halfway. And then for negative 2, e to the negative 2 power, I'm going to write 0.1. I could write 0.14. I'm just going to write 0.1. Again, I don't need to be that accurate. This is close enough for accuracy. So negative 2.1 is just really, really tight to the x-axis. So the graph, just like the last graph, as it goes off to the right, it gets really high very quickly. It goes up and to the right forever. And if I extended this graph up and to the right forever, eventually it'd make it all the way out to the far right edge, or the positive infinity on the x-axis. And in terms of the y-axis, it would also go to positive infinity. So the extension of this graph, this arrow eventually is going to go all the way to the right and all the way up to the double positive infinity. Off to the left, just like the last problem, the y's are always going to be positive. The further, if I did negative 3, negative 4, negative 5, negative 6, these decimals are going to get really small. They're going to be so close to 0 that they're going to be hard to draw. But just like the last graph, it's going to be just slightly above the x-axis always. It'll never touch the x-axis. It'll go on forever to the left. If the proper extension for this, like if I wanted to extend this graph for the domain in the range, it extends all the way to the left of the x-axis, which is negative infinity, and it's always above the x-axis, which is the line y equal to 0. So the y's never even get to 0. They're always slightly bigger than 0. The y's are always positive. So the extension of this graph would be all the way to the left of the x-axis, which is negative infinity. The y's always slightly bigger than 0. So I've made a table of values. I've sketched a graph. I even thought about the extension. So when I answer the domain in range questions, they're easy to do. The domain of this, I find the x-coordinate of the extreme left point, and then the x-coordinate of the extreme right point. All the exponential functions we're going to graph are going to have domains from negative to positive infinity. For the range, I find the y-coordinate of the lowest point and the y-coordinate of the top point. And because the graph never actually touches the bottom point, it's always slightly above it, I'm going to put a round circle and say the range is 0 to infinity again. And the graph, again, the x-axis, which is the equation y equal to 0, when you go off to the left, serves as a horizontal asymptote, meaning the graph never touches nor crosses that line. And the equation of that line that I just drew, the equation of the x-axis, is y equal to 0. So that's not on the homework, but I felt obliged to do a graph of e to the x because it's such a common function. If you look at the graph of e to the x, and then you compare it to the graph of 3 to the x, they hardly look different. As a matter of fact, if you look at the tables aren't that different. Instead of having the 0.29, I have 27.4, 1, 3, 1, 2.7, 0, 1, 0, 1 again, negative 1, 1/3, which is 0.3, negative 1.4. So because the y's are similar, the graphs look very similar. In fact, from my perspective, if I just glanced at these, I couldn't even tell the graphs apart. And that's common. Most exponential functions, when the exponent is just x, kind of look this way. Okay, more graphing. Next one is graphing e to the x minus 3. I should talk before I graph about transformations, because this one asks me to make a table of values, find the domain, the range, the horizontal asymptote, and then it tells me to describe the transformation from e to the x. And so for exponential functions, we can shift them left or right, we can shift them up or down, and we can reflect them above the x-axis or reflect them above the y-axis. This is something you should just know before I get into this problem. So we'll just say, you know, movements or transformations of exponential functions. So if in the exponent, if I have like x minus some number, it doesn't matter what the base is. But if I have an x minus some number, which just is e to the x minus 3, if in the exponent I have an x and then a minus some number, the graph will be shifted to the right that many units. In the one we're going to wind up doing here, the graph is going to be shifted to the right 3 units. So when I'm describing a transformation, comparing the graph of an exponential function to a standard function, if in the exponent there's an x minus a number, the graph is going to be moved to the right, whatever the minus is. In this case, we're going to do 3 units. If I had exponential functions like 2 to the x plus some number, or 3 to the x plus some number, or maybe e to the x plus 6, that would be something that would cause a graph to be shifted to the left. So to move exponential functions left and right from a base graph, you do something with the exponents. Minusing a number in the exponent shifts the graph to the right. Adding a number in the exponent shifts the graph to the left. To move an exponential function up and down, you add afterwards. So if I do like 2 to the x plus some number, or 3 to the x plus some number, or e to the x plus 7, if that plus some number isn't in the exponent, but it's after the function, that's going to move the graph up. So this particular graph would be the same as the graph of e to the x, but shifted up 7 units. If I subtract a number, it's going to move it down. So if I do something like, 2 to the x minus some number, 2 to the x being a base exponential function, or common exponential function that I might move, or 3 to the x minus some number, or e to the x minus 11. This, where the minus comes after the function and isn't in the exponent, it's going to shift the function down. This e to the x minus 11, this would have the same shape as e to the x, but be moved down 3 units. So let me describe the e functions that I have. This function right here, the graph would be the same as the graph of e to the x, except it's going to be shifted to the right 3 units. So making a minus in an exponent, it will move it right. Whereas this one down here, this would have the same graph as e to the x, but it's going to be shifted not to the right, but down 11 units. So minuses will either move the graph right or move the graph down. The minus is in an exponent, it moves the graph right. If the minus is not in the exponent and just subtract it after the function, it moves it down. Pluses to do left or up. This plus, because it's supposed to be in an exponent, this is going to be the same graph as e to the x, but it's going to be shifted. In this case, it's going to go left. And this e to the x plus 7, because the 7's not in the exponent, it's after the function, it's going to be the same as the graph of e to the x, but it's going to be shifted up 7 units. So pluses and minuses, just like parabolas, move the graph left or right, up or down, depending on where the plus or minus is. And that's new but kind of similar. You can kind of think of an exponent like a parenthesis in a parabola in some sense. The other things we have are negatives, and there's two kinds of negatives, and there's one negative that will reflect the graph over the y-axis, the other over the x-axis. This kind of negative, 2 to the negative x, 3 to the negative x, 4 to the negative x, e to the negative x, that movement making a negative x in the exponent with the x, that's going to reflect the graph over the y-axis. And the last kind of movement, putting a negative in front of the function, that's going to reflect the graph over the x-axis. So we have the same movements that we had with parabolas or in the other chapter that we did, transformations. We can move a graph left or right, we can move a graph up or down, we can reflect the graph over the y-axis or reflect the graph over the x-axis. So with that warm-up, when I go to graph this next function, its graph is not going to look radically different than the graph of e to the x. In fact, if I graph them on the same axes, maybe you'll see the transformation better. So I'm going to attempt to do that. So as I go to do problem 4, graphing f of x equals e to the x minus 3, the table of values I'm going to use, so this, I just did f of x equals e to the x. Now I'm going to do f of x equals e to the x minus 3. The table of values I'm going to make for that, because the exponent isn't just an x, I'm going to take the number in the exponent, change its sign, and put numbers bigger and smaller. So the table is not going to be the same. The table that I use for the first two graphs is different than the table for this graph because the exponent isn't just an x. When the exponent's just an x, I use the 2, 1, 0, negative 1, negative 2 table. If the exponent has a minus in it, I change the sign, put that number in the middle of my table. And now I'm going to start getting my y's. For the first y, I'm going to put a 5 in for the x. I get e to the 5 minus 3. E to the 5 minus 3 is e squared. Magically, I don't need my calculator because I've just figured out that e squared is 7.4. So the first point on this graph is going to be the point 5 and then 7.4. So I can barely graph this, but you can see the shifting to the right because here's the first point that I plotted, and this is the point in e to the x, this is the point in e to the x minus 3, and this point is exactly 3 units to the right. Instead of 2, 7.4, it's 5, 7.4 because it's shifted to the right, and shifting to the right changes the x but not the y's. The next point I'm going to plot is e to the 4 minus 3. E to the 4 minus 3 is e to the first power. E to the first power is 2.7. So the second point I'm going to plot is 4, comma, 2.7. So I go over 4 up 2.7. And then similarly, if I compare the point that I drew, 1, comma, 2.7 and 4, comma, 2.7, the y's are the same. The reason we say it's shifted 3 to the right is because the x's are 3 apart. The difference between 1 and 4 is 3, and the 4 is to the right as opposed to the left. The next point, e to the 3 minus 3, is going to give me e to the 0, and e to the 0 power is 1. So I'm going to plot the point 3, 1. And the point 3, 1 is similar to the point 0, 1. It has the same y's, but its x is 3 bigger, so it's shifted 3 to the right. That's why I say this graph is shifted 3 to the right. The last two, I go e to the 2 minus 3. E to the 2 minus 3 is e to the negative 1. I wrote e to the negative 1 to be 0.4. So I'm going to plot the point 2, comma, 0.4. I can't barely even write that, but that's about there. And then lastly, e to the 1 minus 3 is going to be e to the negative 2, and e to the negative 2 I say is 0.1, so 1 comma 0.1. And again, I don't, because I'm copying this on another graph, I don't really have the room to write the points in. But now I can sketch this graph. Off to the right, it shoots up fast and gets high very quickly. Off to the left, it still is going to be bound by the y-axis, and the graph is still never going to go above the below the y-axis, no touch the y-axis. So here's a graph of both e to the x in red and e to the x minus 3 in black. When I go to answer the domain range questions, they're going to be the same answers. These graphs have the same domain in range because for the domain, they both go all the way to the left and all the way to the right, unbroken. For the range, neither graph goes below the x-axis, but they shoot up to the top. And it'll have the same horizontal asymptote. That horizontal asymptote that I drew for e to the x still holds. So when I go to answer the questions that are related to this, find the domain, all exponential functions that we're going to graph are going to have domains from negative to positive infinity. This graph exists from above the x, just slightly above the x-axis, all the way to the top of the y-axis, which we say is 0 to infinity. And the graph never touches nor crosses the x-axis. The x-axis has the equation y equal to 0, and that's the equation of my horizontal asymptote. So that's 2 for 1 on that. I figured that wouldn't be so hard to graph. As a matter of fact, let me see if my calculator can do these very well. Let me graph y equals, I'm going to do e to the x, so second and ln, e to the x, and so this is just, I'll do a zoom standard because I don't know where my graph window is at. So this is my calculator's version of e to the x. My calculator does a horrible job because it makes it look like the graph stops, but the graph doesn't stop. Let me do e to the x on my computer program so you can see that the graph doesn't stop. My calculator, because it doesn't really show the pixels so well, it doesn't have enough resolution, it can't show the graphs as nicely as they need to be shown. On this computer program, if I make the axis back to something normal, and graph e to the x, you'll see that the graph really doesn't stop. It goes forever to the left. Whereas my graphing calculator makes the graph look like it stops. Now I'm going to graph e to the x minus 3 just so you can see them on the same axis. And it's the same shape, second and ln, and then x minus 3. When I hit graph, you won't be able to tell so much the difference except to the right of the y-axis, because both graphs eventually get so close to the y-axis that you can't distinguish the graph between the y-axis. My calculator makes the graph look like they stop, but they don't stop. They actually go on forever to the left, and they're always slightly above the y-axis. All right, so that's probably good enough there. Oh, describe this transformation. This thing is going to have the same shape, or it's going to be the same as the graph of e to the x, except it's going to be shifted to the right 3 units. And you can see that in my graph. At least you can see it clearly to the right of the y-axis, but maybe not so much to the left of the y-axis. It makes it harder to see those things. 6, I'd like to do this graph on the same axes, but I don't have room. I'm going to make a table of values and sketch a graph. And again, I look to the exponent. Because this exponent has a plus in it, when I go to answer this question, I know that the graph is going to be moved to the left. Part E, this graph is going to look the same. It's going to have the same shape or the same appearance as e to the x, except it's going to be shifted to the left 2 units. Let me graph both of these on my calculator just so you can see that real quickly. Let me clear out the e to the x minus 3. So there again is the graph of e to the x. And I'll do e to the x plus 2 on the same graph. And you're going to see that that's shifted to the left 2. So now when I hit graph, I get a graph, but it's over 2 to the left as opposed to going to the right or going down or up. So this is a picture that I'm going to get by hand of e to the x plus 2. Same graph, but shifted to the right, left 2, should I say. It's going to be really nice to know some values of e, because when I go to graph, these values come up a lot. These values that I have right here, that e squared, equals 7.4 rounded to 1 decimal. E to the 1 equal 2.7. E to the 0 equal 1. E to the negative 1 equal 0.4. E to the negative 2 equal 0.1. That's going to be it'd be nice even to have those memorized in some sense. If you take brief calculus, you probably wind up memorizing those. You use them so often. So these values are going to be relevant here. So as I go to graph f of x equals e to the x plus 2, I'm going to make a table of values. I take the number in the exponent, I change its sign, and I take numbers bigger and smaller and fill up the x column. The first y, I'm going to go e to the 0 plus 2. E to the 0 plus 2 is e squared, and e squared is 7.4. So next to the 0, I'm going to write 7.4, and I'm going to plot the point 0, 7.4 the best I can. At least I have the 0 part right, and 7.4 is at least between 7 and 8. And then when I go e to the negative 1 plus 2, that gives me e to the first. E to the first is 2.7. So I'm going to write negative 1 comma 2.7. So negative 1 and then 2.7. I'm not going to write the coordinates because it gets too messy maybe. E to the negative 2 plus 2 is e to the 0. Anything to the 0 power is 1. So negative 2 comma 1. E to the negative 3 plus 2 is e to the negative 1. E to the negative 1 is 0.4. So negative 3 and 0.4. 0.4 is positive. It's slightly above the x-axis again. And then e to the negative 4.2. That gives me e to the negative 2. E to the negative 2 is 0.1. So I'm going to get negative 4 comma 0.1. Just like the last few functions, when my graph goes off to the right, it gets really high really quick. If I extended this graph, it would go all the way to the right and all the way to the top of the y-axis. It would extend to the double infinities. Off to the left, as most exponential functions, the graph goes on forever to the left. It stays slightly above the y-axis, never touches the y-axis. The extension to the left of this graph, it goes to the point negative infinity 0. So this is a picture, a reasonable picture of f of x equals e to the x plus 2. If you graphed e to the x on the same coordinate system, you'd get that. You'd get that graph that's 2 over to the right. So that's a table of values, and I sketched a graph. The domain for all the exponential functions we're going to do, they exist unbroken everywhere to the left and to the right on the x-axis. For the range, the bottom y for my range is the y-coordinate of the horizontal asymptote, which is 0. And for the top y, it's infinity. And the horizontal asymptote, again, just like the first few problems, is still y equal to 0. For problem 8, I threw this 2 in here to make it different than problem 7 or 9. It's a parallel problem. I'm going to make a table of values and sketch a graph. The big thing about the change, this is going to basically have the same shape as e to the x. The negative in the exponent is going to reflect it about the y-axis. The 2 is going to stretch it, but we're not going to worry about the impact of that 2. So if I sketch e to the x, which I already have graphed, and 2e to the negative x, the graph's going to be flipped over. Let me just graph e to the negative x, and then I'll put the 2 in there. So just doing the negative x part, what it does is it flips the graph over the y-axis. You can see that the new graph is reflected over the y-axis. When I put the impact of the 2, then the y-axis won't be a perfect mirrored image. If I look at e to the x and e to the negative x, you get a perfect mirrored image on either side of the y-axis. The 2 is going to distort it. It's going to stretch the graph out. When I graph 2 second ln e to the negative x, then you're not going to see a perfect mirrored image. It is going to be reflected over the y-axis still, but you start to lose. See how it's not perfect anymore? It gets steeper. It gets stretched. It gets pulled higher quicker. So the 2 makes it not a perfect mirrored image. It takes this half and makes it get higher quicker. It stretches it vertically, we would say. But I'm not going to worry about the impact of that too. But if you wanted to, and you can say and, if you could actually write that, and it's stretched vertically. If you wanted to do that, that would be more appropriate than just saying it's reflected about the y-axis, because it isn't just a perfect reflection. It's a reflection and it's skinnier, it gets higher quicker. My table of values, because the exponent doesn't have a plus or a minus in it, I can still use the 2, 1, 0, negative 2. It's not, it has a minus, but it's not x minus some number or x plus some number. So when I go to graph this by hand and get my table of values, this function f of x equals 2e to the negative x, the table I'm going to use is just going to be 2, 1, 0, negative 1, and negative 2. Anytime there isn't a plus or minus after the x in the exponent, this table is going to be okay. So I'm going to go 2e to the negative 2, 2e to the negative 1, 2e to the negative 0, and negative 0 is just 0. So when I do this, I'm actually just going to go 2e to the 0. And then when I do 2e to the negative 1, the negative from the formula and the negative from the 1, that double negative is going to go positive. I'm going to write 2e to the first. And then my last one, I'll go 2e to the negative negative 2. Double negative is going to give me 2e squared. So for my y's, I'm going to use my calculator to find those 5 values. These 3 here, or these 2, I'll do just like that. And then for these 3, I'm going to do them like that and get rid of that double negative. And I can't do these y's without my calculator so well. So let me clear. Second 2 second ln negative 2. So there's 2e to the negative 2. And this calculator's just sometimes so hard to get a window. There's a better one. And that gives me 0.2, and I'm rounding to 1 decimal. I'm going to say that's 0.3. If you round to 2 decimals, that's okay. Now I'll go 2 second ln negative 1, and I get I'll just write 0.7. And all of a sudden I'm waiting to graph, but that's okay. I'll graph all these points at once. And then 2e to the 0 gives me 2. Then 2e to the first, which happens for that point, gives me 5.4. And then 2e squared gives me 14.8, I'm going to write. So there's my table of values. I'm going to sketch a graph. First I'm plotting the point 2 comma point 3, which is about there. And then 1 comma point 7, it's a little bit higher over to 1. 0, 2, negative 1, 5.4, negative 2, 14.8 was maybe up here somewhere. So my graph is going to look something like this. And just like the other graphs, the graph is going to go on forever, but this graph is going to go off to the right as opposed to the left because it's reflected above the y-axis. So the part that was going to the left now goes to the right. The reflection makes it go the opposite way. If I extend this graph, it goes all the way to the far left edge of the x-axis and all the way to the top of the y-axis. That's the left extension. The right extension goes all the way to the right edge of the x-axis, which is infinity. It never goes below 0 or on the x-axis, or for the y's never go below 0. So the domain again is going to be negative infinity to positive infinity because the x coordinates of the extended graph are negative and positive infinity. For the range, I go bottom to top. It's going to be the same range. The bottom y is 0, the top y is infinity, and I have the same horizontal asymptote. It's not till I shift a graph up or down does my horizontal asymptote change. So when I go to answer the parts about the domain and the range, the graph exists everywhere unbroken left to right, so the domain is negative to positive infinity. The graph only exists in this region from y equal to 0 up to the top y infinity, so we get 0 to infinity for the range, and the horizontal asymptote is still that y equal to 0. So as I go to write up my solutions to this, the domain for all these exponential functions are negative to positive infinity, If a graph isn't shifted up or down, the range is 0 to infinity. The horizontal asymptote, if the graph isn't shifted up or down, is y equal to 0 for all of these. So that's everything there is for number 8. 10 throws the negative in front of the e, and that's going to reflect it over the x-axis. So again, if I graphed e to the x and just negative e to the x without the 2, you'll see there's the graph of e to the x, and this is going to be reflected over the x-axis. So the graph of negative e to the x is a perfect reflection over the x-axis. Making that 2 is going to make it stretch. It's not going to be a perfect reflection anymore. So if I hit y equals and I change this to negative 2 e to the x, I still get reflected over the x-axis, but it's kind of stretched. We say that it gets skinnier in some sense, or it goes down quicker. So now it's not such a perfect, the top and the bottom images aren't perfect mirrored images of each other. They're close, but they're not perfect. So in terms of the transformation, the negative reflects it, the negative in front of the 2 reflects it over the x-axis. And I can say it's stretched if I want to, but you don't have to say that. The 2 stretches it. We can say it's stretched vertically, but the 2 stretches it. The domain, the range, and horizontal asymptote, I know what these are going to be. Because the graph isn't shifted up or down, left or, it's not shifted at all, the domain is going to be negative to positive infinity, the range is going to be 0 to infinity, and the horizontal asymptote is going to be y equal to 0. That's the case for all the problems until they're shifted up or down. If they're shifted up or down, then the range and the horizontal asymptote change, but the domain doesn't change. So the table of values that I'm going to make when I do this, f of x equals negative 2 e to the x, because the exponent doesn't have a plus or a minus in it, I'm going to do 2, 1, 0, negative 1, and negative 2. I'll go negative 2 e squared, negative 2 e to the first, negative 2 e to the 0, negative 2 e to the negative 1, negative 2 e to the negative 2. That's just changing that x to those 5 numbers. And again, because there isn't a plus or minus in the exponent, I use that for my table. I'm going to get all the y's real quickly. And if I want to super cheat, let me just do this. Y equals, clear out that function. So that function is the only function in my y's. I'm going to go second table, and next to the 2, the y needs to be negative 4. Oh, I don't have the problem in right. Negative 2. It does. It is because it's reflected over the x-axis. Duh. So the graph is going to look like that. And when I go to do this, my range, I actually have the wrong range on this then. I'll have to go back and fix that. But let me do the y's real quick. Doing second table, the range, or the y's, next to 2 I see negative 14.78, and I'm going to write negative 14.8. So I'm not cheating, but I'm being clever and getting the y's from my table on my calculator. Next to the 1 I need negative 5.4. Next to the 0 I need negative 2. Next to the negative 1 I'm going to write negative 0.7. And then next to the negative 2 I'm going to write negative 0.3. So that would be a quick way to get the y's. Or I could do each one of these separately. Like if I did negative 2 second ln e squared and hit enter, it's going to give me this negative 14.8, and I can get the y's one at a time, or I can cheat on my calculator a little bit. So the first point, 2 negative 14.8, because my graph only goes down to negative 10, I'm going to call that negative 14.8. And then 1 negative 5.4 is somewhere between negative 5 and negative 6 in terms of the y. And then 0 negative 2, negative 1 negative 0.7, and negative 2 negative 0.3. The graph in this case is actually always below the x-axis. So this would be a reasonable graph. It extends all the way to the left, to the point negative infinity, comma 0. It goes all the way to the left, all the way up to the y equal to 0. And off the bottom, it goes all the way down and all the way to the right. The all the way to the right of the x-axis is positive infinity. The all the way down is negative infinity. This still has a domain of negative to positive infinity, but I messed up on the range. This right here is going to be the bottom y for my range. And I always write range as bottom to top. So my range should really be negative infinity to 0. It's not going to be 0 to infinity. For a range to be 0 to infinity, the graph could only exist above the x-axis, but because this graph exists only below the x-axis, it's going to be appropriate to say the range is from negative infinity to 0. So I'll fix that answer, because that range is completely not, that range is okay for number 8, but for number 10, that is not the range of this graph. When a graph exists only below the x-axis, its range is negative infinity to 0. The y-axis, or the x-axis, which is y equal to 0, is still the horizontal asymptote. The graph still never crosses nor touches that as it shoots off to the left. So this, again, is the horizontal asymptote. That part was okay, but my range at 0, saying 0 to infinity, basically says the graph only exists above the x-axis, which is wrong because the graph only exists below the x-axis. So negative infinity to 0 would be appropriate for that. And that's everything for that problem. Okay, finally something that has a shifting that's up. This 2 that shifts the graph up 2 units, what it's going to do is it's going to shift the horizontal asymptote up 2, and it's going to shift the range up 2. It's not going to impact the domain. The domain for every exponential function is going to be negative to positive infinity, but this graph is going to have a different range and a different horizontal asymptote because of this plus 2. Let me show you that, and so I can get these answered. So when I graph, let me graph e to the x, so second ln e to the x, just your generic e to the x function, which has a horizontal asymptote at 0. This is actually going to have a horizontal asymptote at 2 because it shifted up 2 units. So when I go second in ln and do y equals, and then y2, second in ln e to the x, close my parentheses, and then plus 2. When I hit graph, the graph is 2 units above the old graph, and it actually shows the whole graph. On e to the x, because the graph is basically on top of the x-axis, it can't distinguish the graph between the x-axis, but this graph it does show you. And what it shows you is the graph, the bottom of this graph is at 2. The range is going to be from the bottom of the graph, the y-coordinate of the bottom of the graph is 2, and the top of the graph goes to infinity. So for this particular problem, because it's shifted up 2, the bottom of the range gets shifted up 2, and the range for this is going to be 2 to infinity. The horizontal asymptote is going to be at y equal to 2. So when I go to get this graph, you'll see that the graph doesn't go beneath 2, and so that the range starts at 2 and the horizontal asymptote is at 2. This graph doesn't get close to the y-axis. So when I graph f of x equals e to the x plus 2, the table of values I'm using is still the 2, 1, 0, negative 1, and negative 2. The reason I'm using that table still is because the plus isn't in the exponent. So now I'm going to get the y's. I'm going to cheat to get my y's. I'm going to clear out the e to the x function so that the only function is e to the x plus 2, and do second table. And at 2, I'm going to write 9.4 next to the 2. At 1, I'm going to write 4.7. At 0, I'm going to write 3. At negative 1, I'm going to write 2.4. At negative 2, I'm going to write 2.1. Plot those points. And the next point, for what it's worth, at negative 3, it would have been 2.05. At negative 4, it'd be 2.02. At negative 5, it would be 2.001, or 6, 7. So if you look at the y's are always bigger than 2. That's why I say the range is from 2 to infinity. And this graph is never going to go beneath 2. The typical exponential functions never go beneath 0, but because this is shifted up 2 units by that plus 2, this is going to be have a range of 2 to infinity and a horizontal asymptote, not at y equal to 0, but at y equal to 2. The shifting up 2 moves everything up 2. So I go to plot the points. 2 and 9.4 is about there, not perfectly there, but close enough. 1, 4.7 is about here. Again, not perfect, but close enough. 0, 3 is here. Negative 1, 2.4 is about there. Negative 2, 2.1 is about there. Negative 3.2.05 is so close to that dashed line that you couldn't distinguish the two. And this graph is going to look something like this. It goes up really fast. When you extend it up and to the right, you go to the double infinity. But if you extend it all the way to the left, you go to the negative infinity, comma 2. It goes to all the way to the left edge of the x-axis, which is negative infinity, but it never goes beneath y equal to 2. So this would be a reasonable graph for part A. I made my table of values, stole them from my calculator. I'm content doing that. And answering the questions, the domain is still negative to positive infinity, but the range starts at 2, and the horizontal asymptote is at 2. And this explanation, this graph has the same shape as e to the x, but it's shifted up 2. Or I just wrote up 2. That kind of implies shifted up 2. That would be completely an adequate answer for all the parts of number 12. The next parts, all I'm supposed to do is describe the movements without actually sketching graphs. So I can explain the movements by just understanding how movements are created without actually sketching a graph. So from each one of these functions, each one of these is going to have the same shape as 2 to the x because they all have a 2 to the x in them as opposed to e to the x. And they're going to be either moved left, right, up, or down, shifted, or reflected above the x-axis or y-axis. This one is going to, this graph right here, it's going to have the same shape. If I graphed 2 to the x and they'd have the same look. The plus 1 is going to move it 2 to the left, but, so I'll say except it's shifted left 1 unit. And that's all there is to do for that. That's an overly ambitious answer, writing way more than I have to. I'm going to delete all this part and just talk about the shifted. As a matter of fact, I'm going to get super lazy. This plus 3 is going to move the graph left 3 units because it's in an exponent. In an exponent, you can do plus moves it to the left, minus moves it to the right. And you could add all these words. Say it's the same shape as 2 to the x, except it's shifted 1 unit to the left. Ultimately, this is the part that's important. The rest of this, although it's important, it's going to be the same for every problem. I'm not going to write it down. Part C, the minus in the exponent, moves it to the right. And again, I could say this is the same shape as 2 to the x, except it's shifted to the right 1 unit, but I don't need to. The minus 4 in the exponent. Again, in the exponents, it's left or right. Positive is left, negative is right. So these first 4 problems show the left and right movements. Pluses in the exponent moves it left. Minuses in the exponents move it right. These next 2 problems, the plus 3 and the plus 1, aren't part of the exponent. So in that case, the plus moves it up. Minus would move it down. So E, the graph of E would have the same graph as 2 to the x, except it would be shifted up 1 unit. The graph of F would have the same graph of 2 to the x to be shifted up 3 units. G and H are the downs because they're minuses, but they're not in the exponents. And that will move a graph down that many units. Part G, the graph would go down 3 units. Part H, the graph would go down 5 units. I and J have my negatives. A negative to the left are not in the exponent, reflects it over the x-axis. A negative in the exponent reflects it over the y-axis. So up through J, each of the problems only had 1 movement. Left, right, up, or down, reflected over the x-axis, reflected over the y-axis. k has two movements. The plus 1 in the exponent moves it left 1. The minus 4 that's not in the exponent moves it down 4. Again, I'm being very short as to what I'm writing, but I'm writing the important part, the description of the movement that makes this different than the graph of 2 to the x. Part L, the minus 3 in the exponent moves it right 3, and the plus 5 moves it up 5. The m, apparently, I couldn't blow it up for some reason, so I wrote it big here. This negative reflects it over the x-axis, because it's not a negative in front of the x. And because the 3 is in the exponent and not after it, it's going to go right 3. In part n, the negative, because it's in the exponent, it's going to reflect it over in front of the x. It's going to reflect it over the y-axis. The minus 4, because it's not in the exponent, it's going to move it down 4 units. Part O has double negative. The negative in front of the 2 reflects it over the x-axis. The negative in the exponent reflects it over the y-axis. This one I probably should write differently. I should probably write this as negative 2 to the x minus 4 plus 3, so you can kind of see a more standard writing. The negative in front of the 2 reflects it over the x-axis. The minus 4 in the exponent shifts it to the right 4, and the plus 3 moves it up 3. So that had 3 movements in it. So those kind of follow the rules that I tried to illustrate a little bit earlier, talking about how do you move something left or right. Left and right is in the exponent. Minus in the exponent is right. A positive in the exponent is left. Up and down comes after the function, not in the exponent. Minus is afterwards, move it down. Plus afterwards moves it up. Negative in front of the x in the exponent reflects it over the y-axis. Negative in front of the base reflects it over the x-axis. So now we have a bit of algebra to do. And some of the algebra can get a little bit tricky. Each of the problems between 16 and 33, with a bit of work, we'll be able to write both sides with the same base. In problem 16, my goal is to write 27 as 3 to some power. So I'll make a prime factor tree for 27 to see what 27 is as written as 3 to some power. A prime factor tree for 27 tells me that 27 equals 3 times 3 times 3. So 27 can be written as 3 to the third power. My goal for each of the problems between 16 and 33 is to find a value for x that makes the left and the right side the same. A technique that will work for each of the problems from 16 through 33, which isn't the only technique that will work, is to take each side and write them with the same base. If you can write each side with the same bases, then you can drop the bases and get the answer for x by setting the exponents equal. I claim that the answer for problem 16 is x equal 1, meaning if I put 1 in for x, that both sides should simplify to be the same number. So if I go to the original problem that 3 to the x plus 1 equals to 27, it should be the case that 3 to the 1 plus 2 equals to 27. I'm going to be ultra lazy and use my calculator. I'm going to go 3 up arrow 1 plus 2. Put that in the parentheses. There's 3 to the 1 plus 2. When I hit enter, it says 27, because when I put what I think my answer is into the original problem, because both sides simplify to the same number, my answer is correct. So the answer to 16 is 1, and I checked anytime you have a problem with an equal sign, you get a numerical value, expect to get a numerical answer, you can check that numerical answer. 18, I need to be able to write 64 as 4 to some power. That's the nicest way to be able to do it. Unfortunately, 4 is not a prime number, but let me try to break 64 down into 4s. The reason 4 is because the left side's already 4. So I'm going to go 4 times something is 64. To figure that out, I'm going to go 64 divided by 4, and that gives me 16. And now I'm going to write 16. I'm going to try to make a couple 4s out of it, and 16 is 4 times 4. So 64, this is not a prime factor tree because 4s aren't prime, but it's an effective factor tree because this tells me that 64 is 4 to the 3rd power. Because I was able to write both sides with the same base, I can solve or get a value that works for x by dropping the bases and setting the exponents equal. So I drop the 4s and set negative x equal to 3. I'm going to divide both sides by negative 1. On the right-hand side, the two negatives are going to cancel to become a positive. That's going to give me x. On the right-hand side, a positive times a negative is a negative. I claim the answer is x equal to negative 3. I should check. By checking, I'm going to go into the original problem, which is 4 to the negative x equals to 64. Change the negative x to a negative 3. That gives me 4 to the double negative 3 equal to 64. That double negative I can make positive. That gives me 4 cubed equals to 64. That I don't need my calculator for, but I could go 4 up arrow 3. And when I do 4 up arrow 3, I get 64 equal to 64. Because when I take the answer that I came up with and put it into the original problem, because both sides come out to be the same number, my answer is correct. 20, I'd like to write both sides as 1/2 to some power because the left side's already 1/2 to some power. So I'm going to leave 1/2 to the x plus 3 how it is. And I'm going to write 32 as 1/2 to some power. My goal for each of the problems between 16 and 33 is to write each side to the same base. And since I already have a base, I'd like to get the left and the right side to have that same. So I'm going to try to write 1 over 32 as 1/2 to some power. I'm going to do a prime factor tree for 32. 32 is 2 times 16. 16 is 8 times 2. 8 is 2 times 4, and 4 is 2 times 2. So I can take 1 over 32 and write it as 1 over, and there's 1, 2, 3, 4, 5. 32 by itself is 5 2's being multiplied. So I can write this as 1 over 2 to the 5th. And I know that 1 is still the same as 1 to the 5th. So I can write 1 over 32 as 1 over 2 to the 5th, because 1 is still 1, 2 to the 5th is 32. Or 1 to the 5th over 32, because 1 to the 5th is 1, 2 to the 5th is 32. And 1 to the 5th over 2 to the 5th can be written as 1/2 to the 5th. So it took a lot of work that you might not be familiar with, because we haven't done too much exponents recently, to get each side written with the same base. But once I can get each side written with the same base, then I can solve the problem by dropping the bases and setting the exponents equal. And so each of the problems between 16 and 33, they want me to do this. And this is good practice because I'm pulling up some exponent skills that come from beginning algebra that you just might not remember. And that's going to be super common in calculus, that you're going to need to draw on a skill that you haven't seen for 6 months or a year, but you're going to be expected to remember. So just doing this is good. So going through this painful method to solve these is actually kind of beneficial in terms of it's forcing you to remember things quickly that you might have forgotten. So now I'm going to check this. The original problem said 1/2 to the x plus 3 equals 1 over 32. I'm going to put in 2 for the x, and then is it going to be the case that 1 over 2 to the 5th is 1 over 32? I'll do that on my calculator. And on my calculator, I'm going to go parentheses, 1 divided by 2, up arrow 5. I'm going to hit enter. I get a decimal. I hit math, enter, and enter turns a decimal into a fraction. This says 1 over 2 to the 5th is 1 over 32. So when I plug the number in that I think the answer should be, which is 2 for x, and simplify each side, they both come out to the same number. So my answer of 2 is correct. So this again, 20, has an answer of x equal to 2. This problem actually could be solved using logarithms, and it's probably easier to solve using logarithms. We haven't done logarithms yet, which makes it probably wouldn't have been appropriate to solve it with logarithms. And on top of it, this strategy for solving is a good strategy to be able to learn, because you might need to see it again. So 22, it might be nice to write 16 as 1/2 to some power. That's going to be a major challenge. Or I can tweak both sides. Both are ugly. Logarithms would make this a lot easier, but I don't have logarithms at my disposal. Let me work on the 16 and see if I can get 16 equal to some 1/2 power. 16 is 4 times 4. 4s are 2 times 2. The prime factoring for 16 is 2 times 2 times 2 times 2, which is 2 to the 4th power. I'm kind of, well, I know how to make that into a 1/2, but that's something that's too complicated. 16, I'm not comfortable getting 16 as 1/2 to some power. So can I clean up the left side and make the left side 2 to some power? Because it's not easy for me to make 2 to the 4th equal to 1/2 to some power. So the question is, can I make the left side have 2 for its base? Because if I can make both sides have the same base, then I can drop the bases and equate the exponents. And it doesn't matter what the base is as long as they're the same. I'm having a problem getting 16 written as 1/2 to some power, but I can work on this right-hand side, left-hand side, and good things will happen. On the left-hand side, 1/2 is the same as 2 to the negative 1 power. That's something I just pulled out. I don't know if I really pulled that out, but if I do 1 divided by 2, I get 0.5. If I go 2 up arrow negative 1 power, I also get 0.5. Or if I do 2 up arrow negative 1 power and then do math, enter, it's 2 to the negative 1. So I can rewrite this problem that says 1/2 to the 2x plus 1 power. I can rewrite that as 2 to the negative 1 to the 2x plus 1 power, because 1/2 and negative 1 are the same. There's a rule of exponents that has said if you have one base that has 2 exponents that apply to it, you multiply the exponents to get rid of that parentheses. So for this, I'm going to multiply negative 1 times 2x and negative 1 times 1 and get negative 2x minus 1. I can rewrite the left side to have a base of 2 because 1/2 can be written with a base of 2. 1/2 to the 2x plus 1 can be written with a base of 2. And it's going to be 2 to the negative 2x minus 1 for that side. So really complicated problem, but good to see complicated because calculus is littered with complications, and seeing the complications now is going to help you and make you a better calculus student. So I was able to write both sides with 2 as a base. I could have done some work to make the 16 have a 1/2, but it seemed harder than doing what I did. Now that I have both sides with the same exponent bases, I drop the exponents, equate the bases. I'm going to add 1 and get negative 2x equals to 5. Divide by negative 2, and get x equals 5 over negative 2, which I'm going to write as negative 5/2 or negative 2.5. Now I need to check. So I claim that this is my answer. It's going to be a lot easier for me to use negative 2.5 when I use my calculator. So I need to make it's that 1/2 to the 2 times negative 2.5 plus 1 equals 16. That's putting negative 2.5, which is what negative 5/2 is, into that. So to do this on my calculator, I'm going to go parentheses 1 divided by 2, up arrow, and then parentheses 2 times negative 2.5 plus 1. So that's exactly doing that properly on my calculator. I put the 1/2 in an exponent. I put the 2 times negative 2.5 plus 1 in an exponent. If when I hit enter, I see 16, I'm doing well because the right side is already simplified at 16. So that means this has to equal 16 or I've messed up. And when I hit enter, it gave me 16 equals to 16. Because that's a true statement, I know that my answer is correct. It's a pretty intense problem. The last two problems were actually kind of complicated, and that's not a bad thing. Like I said, the higher you go in math, the more complicated it gets, and you just need to just figure out, you know, some strategies that you may have not thought of before. 24 and 26 are similar problems in that both sides have exponents, but they're not as complicated because it's not very hard to write 25 as 5 to some power. So I'm going to work on the right side. And I'm going to change the 25 on the right-hand side to 5 to some power. I'm going to put it temporarily in a parentheses. So when I do 25, the prime factor tree is just 5 times 5 because 25 is just 5 times 5 or 5 squared. So in this problem, the 25 I can change to 5 squared. I'm going to put that in a parentheses because I actually have to multiply this 2 by the 3x and the minus 4. So I can change this problem. The left side is fine the way it is written. On the right side, I'm going to multiply the exponents and get 5 to the x plus 2 equals 5 to the 6x minus 8. Now I'm going to drop the bases and equate the exponents. I'm going to minus x from both sides and add 8 to both sides. When I minus x, it cancels on that side. Add 8, I get a 10. On this side, 6x minus x is 5x. 8's cancel. Now divide both sides by 5. And I'm going to wind up getting 2 for my answer. I'm going to check it. To check it, it has to be the case that if I go to the original problem, that 5 to the 2 plus 2 power is going to equal 25 to the 3 times 2 power minus 4. I'm going to do each on my calculator. First, I'm going to do 5 up arrow parentheses 2 plus 2 power. When I do that, I get 625. So the left-hand side, when I put 2 in for x in the original problem, I get 625. That has to be the case to the right-hand side. So on the right-hand side, when I go 25 up arrow parentheses 3 times 2 minus 4, I also should get 625. And if I didn't get 625, my answer wasn't correct. So the nice thing, even though the algebra is calculus, as hard, should I say, the checking's not that hard. And so for all these problems between 16 and 33, if you stumble and you get the wrong answer, you know your answer is wrong, then you know you need to recalibrate and try to figure out what you did wrong. So there's a nicety to this, that the checking is so easy to do that it makes it so I shouldn't ever write down a wrong answer. I'm going to do 26 the same way. I'm going to rewrite the 9 as 3 to the second power because the prime factoring for 9 is 3 times 3. And 9 is 3 to the second power. So for 26, I'm going to say 3 to the x minus 4 equals 3 to the second power times 3 minus x. Now I'm going to multiply my exponents. I'm going to get 3 to the x minus 4 equals 3 to the 6 minus 2x. That's multiplying 2 times 3 and 2 times minus x. Now I'm going to drop the bases and equate the exponents. I'm going to add 2x and 4 to both sides. When I do this, on the left side I get 3x. On the right side I get 10. Put those funky. And then I'm going to divide both sides by 3. And I get x equals 10 over 3 for what I think is the correct answer. Didn't leave myself as much room to check, so I'm going to sneak my checking in right here. For checking, should be the case that 3 to the 10 over 3 minus 4 equals 9 to the 3 minus 10 over 3. Both of these are going to be ugly decimals, which is not so bad. I'd prefer them not to be. They're just going to be that way, though. So I'm going to do the left side. I'm going to go 3 up arrow parentheses 10 divided by 3 minus 4. And when I do that, I get 0.4807. On the right side, I go 9 up arrow parentheses 3 minus 10 divided by 3, close out my parentheses. I get the same 0.4807, and that's what it takes for a solution to be correct. It doesn't have to be that you plug the number in and you get a beautiful integer. You can have ugly decimals equal to each other. That still is correct, as long as my answer that I put in for the x's in the original problem causes each side to simplify to the same number, then your solution's correct. So 26 is correct because checks. 28 is also going to be ugly in terms of the checking, but not so bad. So for 28, because it's written with the same basis, even though the base is an ugly e, I can drop the bases and equate the exponents. I'm going to plus 3 and minus x from both sides. On the left-hand side, the x's cancel. I'm left with a negative 1. On the right-hand side, I get x. I claim that the answer is x equal to negative 1. Shouldn't be that hard to check. Should be the case that in the original problem, e to the x minus 4 equals e to the 2x minus 3. If I go e to the negative 1 minus 4, it should equal e to the 2 times minus 1 minus 3. And I'll just do again both of these mindlessly on my calculator. So first one, second ln, and then negative 1 minus 4. When I do that, I get 0.0067. And then on the right-hand side, I go second ln, parentheses already there, 2 times negative 1 minus 3. And the right-hand side also comes out to 0.0067, and they're exactly the same numbers. That means my answer is correct. My answer would be wrong if when I put this in that the sides didn't come out to the same number. So I think 2 more problems, and they require me to remember a rule of exponents that you may have forgotten. Both 30 and 32 are set up so the left side simplifies. On the left-hand side, in problem 30, I'm multiplying 2 terms with the same bases. To do that multiplication on the left-hand side, you add the exponents and fix the base. So this left-hand side simplifies to e to the 3x plus 2. Now that I've simplified the left-hand side using a rule of exponents, I have the bases the same on each side. I drop the bases, equate the exponents. Here I'm going to minus 2 from both sides and get 3x equal to minus 6. And then I'm going to divide both sides by 3 and get my answer that I believe is correct of x equal to minus 2. Again, I should check this. So I should go to the original problem. E to the 3x times e to the second power, e to the second power equals e to the negative 4 power. I should plug in negative 2 for x. This should be the case that e to the 3 times negative 2 times e squared equals e to the negative 4. I could do this on my calculator. Again, it's kind of mindless on my calculator. So on my calculator for this left-hand side, I do second ln, 3 times negative 2, and close out the parentheses. And just can't seem to find a spot to make this show up without being glaring. And then I'm going to go times second ln squared. So that's the left-hand side. That's e to the 3 times negative 2 times e to the e squared. And this comes out to 0.0183. The other side is just e to the negative 4. So I go second ln negative 4 and hit enter. I get 0.0183 because those numbers are exactly the same. My answer is correct. That's what it takes for an answer to be correct. That when you plug your answer into the original problem, simplify both sides, they simplify to the same number. 32 is essentially the same problem as 30, except the base is 2 as opposed to e. To do 32, I'm going to rewrite the left-hand side by fixing the base and adding the exponents. Because I'm multiplying terms with the same base, you do that multiplication by not changing the bases, but you add the exponents. There's like terms in the exponents. Minus 4 plus 3 equals to minus 1. Now that I have the problem written with the same base, I can drop the bases, set the exponents equal, add 1 to both sides, and I get what I think is the correct answer of 6. Go to check, go to this original problem, do 2 to the 6 minus 4 times 2 cubed equals 2 to the 5th. I'll do the left-hand side mindlessly on my calculator. So we go 2 up arrow parentheses 6 minus 4 times 2 up arrow 3. So the left-hand side simplifies to be 32. The right-hand side, I go 2 up arrow 5. It equals the 32 because when I plug the answer that I got via my algebra in and simplify both sides, because they simplified to the same number, my answer is correct. These style of problems come up again in a couple of sections. So if you didn't perfect them this time, you'll get to see them again. And when we see them again, we'll have logarithms at our disposal. And I might show you how to do some of these harder ones with logarithms, because some of these problems were a bit tedious to do, and logarithms makes them a little bit easier. So be prepared maybe to learn another way that you might like better.